So, we will continue our discussion on IC engine, and today again we will discuss about diesel cycle, Otto cycle, diesel and dual. We have discussed about the Otto cycle, the standard cycle which is used to approximate the different processes in a 4-stroke cycle SI engine is the Otto cycle. Last class we have discussed about the diesel cycle, which is the air standard cycle, which is used to represent different processes in a 4-stroke cycle diesel engine, and we have quantified the thermal efficiency for the diesel cycle, and we have also discussed that Otto cycle is known as constant volume cycle, while combustion process is represented by a constant volume process, while diesel cycle is known as constant pressure cycle, where the combustion process is represented by a constant pressure process. So, if we try to recall that we have seen that efficiency of the diesel cycle, that the thermal efficiency of the diesel cycle can be written 1 minus, that is we did not do a few steps. So, to arrive the final expression, rather I can write the final the expression of the efficiency of the thermal efficiency of the diesel cycle is 1 minus T4 minus T1 if I by T3 minus T2 into K. So, I discussed that if we do more steps, a few more steps, then I will be able to arrive at the final expression, which is nothing but 1 minus 1. So, rather instead of writing the final expression of the diesel cycle, let us first try to do that steps, I mean, so that we can arrive at the final expression. So, you know that we have defined a few terms, that is beta is the cut-off ratio, which is known as cut-off ratio, that is the change in volume during the combustion process, that is constant pressure heat addition process, and that is very important, that is known as V3 by V2. So, beta is equal to V3 by V2 is equal to T3 by T2. Similarly, compression ratio RC, that is defined as the volume VDC by volume TDC, that is V1 by V2. So, that is what we have defined, that is equal to T1, that we will write in terms of ideal gas relationship, fine. So, can we write the thermal efficiency of diesel cycle in terms of these two parameters, that is cut-off ratio and the compression ratio. So, this is the compression ratio. If I try to recall that the PV diagram, that T4 will be equal to, so I can do a few more steps so that we can arrive at the final expression 1 minus T1 into T4 by T1. I can take T1 outside and divide by, again I can take T2 outside, T3 by T2 minus 1 into K. So, T1 by T2 is, so T2, if I use that process 1 to 2 was the isentropic compression process. So, T2 is equal to T1 into V1 by V2 to the power K minus 1, that is equal to T1 into RC to the power K minus 1. That is what I have written. So, therefore, T1 by T2 will be equal to 1 by RC to the power K minus 1. So, I can straight write T1 by T2 is equal to 1 by RC to the power K minus 1 into T4 by T1 minus 1 divided by K into T3 by T2 is equal to beta. So, this is beta minus 1. So, I have to write now T4 by T1 minus 1 in terms of cut-off ratio and the compression ratio. How can I write it? And for that again we need to do a few more steps. So, this is the expression, but still it contains the temperature ratio T4 by T1. So, if I now T4 by T1 I can write T4 by T1, that is very important things, because I have to write T4 by T1 in terms of beta and RC. So, T4 by T3 is what? Because if I can recall that if I try to recall the PV diagram over here, then process 1 to 2 was like this, then 2 to 3 was combustion process, that constant pressure process, and this was 4. So, this is 1, this is 2, this is 3, this is 4. So, this V2 is the VTDC and this is V, this is P. So, this is V2 and this is V4 or V1. So, this is VVDC. So, now T4 will be equal to, that is isentropic expansion. process 3 to 4 is isentropic expansion power stroke. So T4 is equal to T3 into V3 by V4 to the power k minus 1, that I can write, right. So now I can rearrange this term, T3 is equal to V3 by V2 into V2 by V4 to the power k minus 1, or I can write T3 into V3 by V2 into V2 by V4 to the power k minus 1. Now question is, if I go to the next slides, that is T4 is equal to T3 into V4 by V4 by V3 by V2 into V2 by V4, V3 by V2 into V2 by V4 to the power k minus 1. Now question is, what is V4? So if I look at the PV diagram, V4 is equal to V1, that is VVDC. So I can write that T3 into V3 by V2 into V2 by V1 to the power k minus 1. This is what is. So I can write it T3 into V3 by V2 to the power k minus 1 into V2 by V1 to the power k minus 1. So what is V2 by V1 to the power k minus 1, right. So T3 is equal to, now therefore I can write T4 is equal to T3 into V3 by V2 is equal to V3 by V2, T3 into V3 by V2 is equal to beta. So beta to the power k minus 1 into V2 by V1 is equal to what? V2 by V1 to the power k minus 1 is equal to T1 by T2, is equal to T1 by T2. So this is T1 by T2 and V3 by V2 is equal to beta to the power k minus 1. Therefore I can write T4 by T1 is equal to T3 by T2 into beta to the power k minus 1. What is T3 by T2? It is, if I go back to my previous slide, T3 by T2, what is T3 by T2? T3 by T2 is equal to V3 by V2 into beta to the power k minus 1, that is beta into beta to the power k minus 1, that is beta to the power k. So if I replace the value of T4 by T1 in the expression of thermal efficiency, so I can obtain the final expression eta thermal diesel equal to 1 minus 1 upon RC to the power k minus 1 into beta to the power k minus 1 divided by k into beta minus 1. That is what we wrote last class, but without doing this intermediate steps. So without doing this intermediate steps, straight away we have written the final step, that the thermal efficiency of the diesel cycle can be written in terms of compression ratio and the cut-off ratio. Now question is, if I compare, and that is what I have discussed, that if we compare this efficiency with the efficiency of a Otto cycle, where efficiency of the Otto cycle, that the thermal efficiency of the Otto cycle, is equal to 1 upon RC to the power k, right, that is 1 upon 1 by RC to the power k. So this is very important, that thermal efficiency of the Otto cycle is basically 1 upon 1 by RC to the power k minus 1, not k. So if I compare these two efficiencies, I mean Otto cycle and diesel cycle, that we have seen that the beta is always 1, k is always 1. So the quantities in the bracket term is always greater than 1. So for a given compression ratio, efficiency of the Otto cycle will be higher, since the compression ignition engines, rather diesel engines, are normally having higher compression ratio. So the efficiency of the diesel cycle would be higher. Therefore for a given compression ratio, since the quantities given in the bracket is always greater than 1, so for a given compression ratio, efficiency of the Otto cycle will be always higher. But since the diesel engines are having higher compression ratio, so the efficiency of the diesel cycle will be higher than the Otto cycle, and that is why constant pressure combustion, constant volume combustion is more efficient than the constant pressure combustion. That is what we have written. So for the given compression ratio, efficiency of the thermal efficiency of the Otto cycle will be higher than the diesel cycle. So constant volume combustion is more efficient than the constant pressure combustion. That is what we have discussed in the last class. But since diesel cycles are operated at a higher compression ratio, so efficiency of the diesel cycle will be higher. Now question is, another important term is that if these two equations are compared, then we have seen that an ideal engine should be a compression ignition engine, but should operate with the Otto cycle. Why? Because logic is quite straightforward, that since Otto cycle is having higher efficiency and compression ignition engines are normally having higher compression ratio, so an ideal engine and an engine should be operated ideally, rather an engine should be ideally a compression ignition engine and should operate with the Otto cycle. And that is why that the very important that the recent modern diesel engines, is very important that the modern high speed CI engines, rather diesel engines, are accomplishes this by doing a little change in the operating system. How? So that again I am repeating, since Otto cycle efficiency will be higher than the diesel cycle while for a given compression ratio, on the other hand since CI engines are having higher compression ratio, so efficiency of the diesel cycle will be higher. So an engine should be ideally a compression ignition engine, and that would operate with the Otto cycle. So that is why modern high speed CI engines are modified by changing their operating, partly, rather by simple part changing their simple operating, rather the operation principle. That means modern high speed CI engines are operating with a little bit change in their operating system. By how? That we have seen that in a CI engine what is done, that we have seen that we are utilizing the high pressure and temperature, the condition of high pressure temperature of the compressed air, so that the whenever fuel will be injected and combustion will start, and that is why combustion starts late at the compression stroke, only to take into account the ignition delay. I mean, it is not possible that whenever piston will be reaching at that TDC, and if the moment whenever piston reaching at TDC, if we start injecting fuel, combustion will be completed. It won't be the case, because there will be some amount of ignition delay, and although it is of the order of millisecond, but still it is a finite time required to have a final spray pattern of the fuel. It comprising the chemical delay as well as the physical delay. So to take that effect into account, what is done is that fuel is sprayed when piston is little bit away from the TDC, and combustion lasts even when piston is coming traveling from TDC towards VDC, and that is why volume is remaining no longer constant, rather we are assuming the pressure is remaining constant. So since volume is changing little bit, so pressure is remaining constant. That was a good approximation. Now question is, instead of assuming that, if we change a little bit in the operating system, that means instead of injecting fuel late at the compression stroke, rather if fuel is injected maybe when little bit away from the TDC, maybe it around 20 degree below TDC. So whenever fuel is injected, the injected fuel, first part of the injected fuel will be combustion will be completed whenever piston is reaching at TDC. That means if we start injecting fuel in a CI engine when piston is little bit away from TDC, that is 20 degree below TDC, so by that time when piston is reaching at TDC, that time the first injected fuel will start combustion, rather combustion will be completed. So as if whenever piston is reaching at the TDC, that in volume is remaining constant, so part of the combustion is completed at the constant volume process, and remaining part of the combustion will be completed when piston is again traveling back from TDC toward VDC, and pressure will remain constant. That is what we assume for a CI engine. So our idea is that since efficiency of the Otto cycle is always higher than the diesel cycle for a given compression ratio, on the other hand CI engines are normally having higher compression ratio, so an ideal engine should be a compression ignition engine, and that would operate on an Otto cycle. That means that is why modern high speed CI engines are operated with a little bit change in their operating system. By how? So we are injecting fuel little bit away from TDC, which is 20 degree away from TDC. So first part of the fuel whenever injected, that means by the time when piston will be reaching at TDC, the first part of the fuel being injected will complete their combustion, rather the combustion is completed at constant volume. Whenever piston is reaching at TDC, that the volume is remaining constant. So the first part of the combustion is completed when piston is at TDC, that is a constant volume process, while remaining part of the combustion will completed when again piston is coming back from TDC, rather away from TDC, and that time we cannot say that the volume will remain constant, rather pressure will remain constant. So that means if we assume that the part of the combustion or the first part of the combustion is completed at a constant volume process, and remaining part of the is completed at a constant pressure at constant pressure inside the cylinder, that means we are breaking off the entire combustion. Part of the combustion is completed at constant volume, and part of the combustion is completed at constant pressure. So we are utilizing the constant volume combustion, and as I said you that the constant volume combustion is more efficient than the constant pressure combustion. So we may have higher efficiency that the diesel engine, and we can have the total combustion. Since part of the combustion is completed at constant pressure and part of the combustion is completed at constant volume, and this is known as dual cycle. That means this is very important, that what is dual cycle. So analysis of this is very important, that analysis of a CI engine which is done using an air standard cycle, where part of the combustion is completed at constant volume and part of the combustion is completed at constant pressure, is known as dual cycle. So dual cycle is an air standard cycle which represents the processes of a CI engine where entire combustion is completed into two parts. First part is at constant volume and second part is at constant pressure. So now we will need to do and we need to see what is a dual cycle and how we can quantify the thermal efficiency of a dual cycle. So the concept of dual cycle is coming from the fact that the efficiency of Otto cycle is always higher than the CI engine diesel cycle for a given compression ratio. On the other hand, since compression ratio CI engines are operated with a higher compression ratio, of course compression efficiency of the diesel cycle should be higher. So an ideal engine should be a CI engine which would operate on an Otto cycle, and for that the concept of dual cycle is coming, where we are splitting the entire combustion process into two parts. First part is occurring at constant volume process, while the remaining part is occurring at the constant pressure process. So now we would like to see what is the dual cycle. That if a CI engine is operated on a dual cycle, which is now most of the modern high speed engines, CI engines are operated on a dual cycle. So if I draw the PV and PV diagram, so this is PV diagram and we have to draw the corresponding TS diagram. So this is T and this is S diagram. So again I am saying that this is the process, maybe constant pressure air intake. Then what is done is very important, that air is compressed, maybe this is process 6 to 1. So this is process 6 to 1. So this is process 6 to 1, and then so this is process 6 to 1, 1 to 2 is the isentropic compression, 2 to 3 is the first part of the combustion which is occurring at the constant volume. That means in a CI engine fuel is injected when piston is little bit higher from the TDC, that is 20 degree below TDC. That means by the time when piston is reaching the TDC, the first part of the fuel being introduced will complete their combustion, that is at constant volume. The volume is remaining constant because piston has reached at TDC, and the remaining part of the combustion is completed when piston is again traversing back from TDC, that is constant pressure. So 2 to 3 is the constant volume combustion and 3 to 4 is the constant pressure combustion. It is very important. And then again we are having isentropic expansion, and then this is this is 3 to 4 and 4 to 5, 5 to 1 is exhaust blowdown, right. So sorry, so this is, let's say this is point X, I do not know, this is point X and this is point 3 and this is point 4, 3 to 4 is isentropic expansion and 4 to 1 is exhaust blowdown, and or I can say 4 to 5 and 5 to 6 is the exhaust stroke. So if I draw the corresponding TS diagram, process 1 to 2 is the isentropic process, so entropy will remain constant. Then process 2 to 3, 2 to X is a constant volume heat addition process, so temperature will go high, that I do not know. And again X to 3 is again constant pressure heat addition, so again temperature will go high, but we need to know the slope. So this is 3, maybe 3, and then 3 to 4 is again isentropic process, and then 4 to 1 is the 3 to 4 is isentropic process, and 4 to 1 is exhaust blowdown, right. 4 to 1, this is 4 to 1, so this is 1 to 2. So this is the PV and TS diagram for a dual cycle. Why it is dual cycle? Because the combustion is split into two parts. First part is 2 to X, where is a constant volume heat addition. So 2 to X is constant volume heat addition. The combustion is represented by constant volume heat addition, that represent dual cycle, that represent Otto cycle, while X to 3 constant pressure heat addition. This constant pressure heat addition. Now one ratio is defined here, pressure ratio. So just like a CI engine, we have defined cutoff ratio, change in volume, but here we are defining on pressure ratio. What is pressure ratio? Pressure ratio is defined as the ratio of as the rise in pressure during combustion. So this is defined as the rise in pressure during combustion. So what is this alpha? That is Px by Px, or P3 is the peak pressure, so Px by P2, that is the, and that is equal to P3 by P2, that is equal to Tx by T2. So I can write it in terms of compression ratio, that is 1 upon Rc to the power k minus k into P2 by P into P3 by P1 because Tx that is alpha, that is known as pressure ratio. So now we have to analyze thermodynamic analysis to have a quantification of the thermal efficiency. So, as a rise in pressure during combustion is pressure ratio that is defined by alpha Px by P2 that is equal to P3 by P2. So, P3 by P2 is equal to that is equal to what is P3 is equal to Px is equal to Tx by T2. So, that is equal to 1 by Rc into P3 by P1. If I do some, I will get this expression if I do some some analysis, I mean if we do a few more steps. Okay, fine. So, now question is process 2 to x, very important process 2 to x is what is process. So, we have to analyze first process 2 to x. 1 to 2 is very important process, but process x to 3 very straightforward. So, only thing we need to know that heat output and heat input. So, process 1 to 2 is a very straightforward process, I am not going to analyze. So, now we write process 2 to x. So, process 2 to x is a constant volume heat input, that is first part of the combustion. So, as I read you, this is constant volume heat input, first part of the combustion, right, first part of the combustion. So, all valves are closed, all valves are closed. Fine, valves are closed. So, how can I? So, Vx is equal to V2 is equal to Vtdc is fine. What is W2 to x? Constant volume is 0, but what is Q2 to x? So, Q2 to x equal to Cv into Tx minus T2, that equal to, or I can write small q2 to x is equal to Cv into Tx minus T2, Tx minus T2. So, that is Ux minus U2, that is Ux minus U2, and Px is a maximum pressure, Px is equal to P max is equal to P3, right, is equal to P is equal to P2 into Tx by T2. That is what I have written, Px by P2 is equal to Tx by T2. So, Px is equal to P max is equal to P3 is equal to Tx by T2. So, this is the process 2 to x, constant volume heat addition, that is the first part of the combustion where pressure ratio is defined as a rise in pressure during combustion, that is Px by P2 is equal to P3 by P2 is equal to Tx by T2. If we do a few more steps, it is highly possible to arrive at that expression, that 1 by Rc to the power k into P3 by P1, fine. So, next process is, I did not do the analysis of process 1 to 2, process 1 to 2 is straightforward, process 6 to 1 is again straightforward. I did this analysis for the Otto cycle and diesel cycle. Again we are assuming air turbine ideal gas and we are using the ideal gas relationship to obtain the pressure and temperature at the end of each and every stroke, fine. Now process, very important process x to 3. So, process x to 3 is constant pressure heat addition, constant pressure heat addition, and it is second part of the combustion or last part of the combustion, last part of the combustion. So, what is, I said you P3 is equal to Px is equal to P max is the maximum pressure. What is Qx3? Qx3 is equal to Cp into m mass flow rate of mixture into T3 minus Tx, right. So, Qx3 small specific, that is equal to Cp into T3 minus Tx, right, that is equal to H3 minus Hx. What is work done? Wx3, this is very important, constant pressure process, not constant volume process. So, that will be equal to Qx3 heat addition minus U3 minus Ux, minus U3 minus Ux is equal to what? So, Qx3 is equal to work done plus U3 minus Ux, that is equal to P3 is equal to P max into V3 minus Vx, change in volume. So, that is that is equal to, or Px into or equal to P3 into V3 minus Vx, because Px and P3 are equal. So, this is Vx. So, that is Wx3, and T3, if we go back, this is T max. If we go back to my previous slide, it is written that T3 is the maximum temperature in the cycle. So, fine, we have obtained that T3 is equal to T max. So, constant pressure heat addition, again all valves are closed, all valves are closed. So, both the valves are remaining closed, fine. As I defined that Cartop ratio, so Cartop ratio is, again you have to define for this case Cartop ratio, that is change in volume beta is equal to what? Beta is equal to V3 by Vx is equal to capital V3 by Vx is equal to T3 by Tx. So, T3 by Tx. So, this is the cutoff ratio. So, what is the net heat input in the system? That is what we need to know, because ultimately you have to calculate the thermodynamic efficiency. What is the heat input? What is the heat input in the system? So, total heat input Q in, that is at constant volume process plus constant pressure process. So, Cv into, that is Q 2 to x plus Q x to 3 at constant first part of the combustion plus second part of the combustion. So, that is equal to Ux minus U2 plus S3 minus Hx, S3 minus Hx. So, Ux minus U2 is the heat addition in the first part of the combustion, where S3 minus Hx is the heat addition in the second part of the combustion, that is Q2 to x Ux3. That is very straightforward. Fine. So, how can I now calculate efficiency? Because heat output from the system is straightforward. What is the heat output from the system? Now, process 4 to 1 is the process 4 to 1, that is constant volume heat rejections. Constant volume heat rejection, that is what we have derived in the last class. So, what is that? Q out will be equal to Cv into T4 minus T1. Constant volume heat addition, constant volume heat rejection, so Cv into T4 minus T1. So, now if I write the thermal efficiency of the system, so what will be the thermal efficiency of the dual cycle? What is the thermal efficiency of the dual cycle? Very important. So, what is? So, W net by Q in, W net by Q in, that is the thermal efficiency of the dual cycle, sorry. So, that will be equal to nothing but 1 minus Q out divided by Q in. So, what is Q out? 1 minus Cv into T4 minus T1, then divide by what is Q in. This is very important, you have to write what is Q in. So, what is, if I go back to my previous slide, what is Q in? Ux minus U3, that is, so that is what is Cv into Tx minus T2. So, that is Cv into Tx minus T2 plus Cp into T3 minus Tx. So, if I write it, that Cv into is very important, Tx minus T2 plus Cp into T3 minus Tx. So, this is the heat input to the system, while heat output to the system is Cv into T4 minus T1. So, if I do a few more steps, that means I can write T4 minus T1, right, T4 minus T1 divided by Tx minus T2 plus Cp by Cv is equal to K into T3 minus Tx. So, this is the final expression K into. After a few rearrangement, if we do a few more steps, that is what I did in the first half of my lecture for the diesel cycle. That means if we do a few more steps only to have some manipulations only and in terms of some T4 different temperatures, we can write the efficiency, thermal efficiency of dual cycle in terms of cutoff ratio and pressure ratio. However, the final expression for the thermal efficiency of the dual cycle can be given 1 minus 1 upon Rc to the power k minus 1 into what is the first term, is very important, alpha beta to the power k minus 1 divided by k into alpha into beta minus 1 plus alpha minus 1. So, this is the thermal efficiency of the dual cycle. So, I can come from this step to this step, I can come from this step to this steps, and for that we have to do a few more steps, we have to do a few rearrangement, and eventually we will arrive at the efficiency of the dual cycle will be 1 minus 1 upon Rc to the power k minus 1 into alpha to the power beta, alpha beta to the power k minus 1 divided by this quantity. That means we have established the efficiency of a dual cycle in terms of compression ratio, cutoff ratio and the pressure ratio. Fine. So, now question is, that means we have seen, so we have first we have discussed about Otto cycle, where the combustion process is represented by a constant volume process. Second, we have discussed about the diesel cycle, where we have represented the combustion process by constant pressure process. We have seen by comparing the efficiencies of Otto and diesel cycle, we have seen that the efficiency of the dual cycle is always higher than the diesel cycle for a given compression ratio. But since the compression ratio, the efficiency of the diesel cycle is always, Otto cycle is always higher than the diesel cycle for a given compression ratio, but for the diesel cycle, rather for the compression, since the compression ignition engines are having higher compression ratio as compared to that of the SI engines, then efficiency of the diesel cycle will be always higher. And keeping that in mind, it is suggested that an engine ideally should be a CI engine, because it is having higher compression ratio, it should get higher compression efficiency, but it would operate in Otto cycle, because Otto cycle is having higher efficiency than the diesel cycle for a given compression ratio. So whatever is the compression ratio, Otto cycle will always give the higher efficiency. That is why constant volume combustion is more efficient than the constant pressure combustion. Considering that aspect, modern days, modern high speed CI engines are operated using a little bit change in their operational procedure, operating cycle. By how? That is what I have discussed, that what is done during the combustion process for a CI engine. Fuel is injected when piston is late part of the compression strokes. That means piston is very close to the TDC, only to take into account the ignition delay, that is the physical delay plus the chemical delay. But instead of doing so, if we ignite fuel when piston is little bit higher from TDC, that is 20 degree below TDC, so that the first part of the fuel being injected or introduced into the cylinder the combustion of that first part of the fuel being introduced or injected in the cylinder will be completed whenever piston will be reaching at the TDC. That is as if the first part of the combustion is completed at the constant volume, because piston is reaching at TDC, while the second part of the last part of the combustion will be completed when piston is again travelling back from TDC toward VDC. And by this we can split the entire combustion into two parts. First part is the constant volume combustion and second part is the constant pressure combustion. Since we are having a constant volume combustion in this cycle and constant pressure combustion cycle, we are calling it dual cycle. That is, we are having dual combustion, and since we are having a constant volume combustion, so efficiency of the dual cycle should be higher, because it as I said you, the constant volume combustion is more efficient than constant pressure. And we have seen how we can represent the pressure volume change in pressure volume in the during the in the engine cylinder during different stroke in a PV diagram as well as the TS diagram. And from there we have tried to quantify the thermal efficiency of the dual cycle, and for that we have tried to quantify. We didn't discuss about a few processes like process 6 to 1, process 1 to 2, because these are straightforward process. Similarly process 3 to 4, because we have discussed these processes in the context of discussion of Otto cycle as well as the diesel cycle. But here two important processes are process 2 to X, the first part of the combustion when volume remaining constant, while second part of the combustion is the X to 3, that is constant pressure combustion where pressure is remaining constant. And we have included in both these processes we are having heat input to the system. So we have quantified total heat input to the system. On the other hand, process 4 to 1 is the heat rejection process, exhaust blow down. So we have quantified that what is the heat ejected from the system, and doing this we have quantified the thermal efficiency, and we have derived the expression of thermal efficiency in terms of different temperature. But if we do a few more steps, then we will be able to arrive at the final expression in terms of compression ratio, cutoff ratio and pressure ratio. So with this I stop here today, and we will discuss that for a given compression ratio, if we try to compare the efficiency of all these cycles, then we will be able to show that the efficiency of the Otto cycle is greater than dual, greater than diesel. And if we consider that, because compression ratio, so while you are considering a same compression ratio, then we will be able to show that the efficiency of the diesel Otto cycle is greater than dual, greater than diesel. But compression ratio is not same for all the cases, so compression ratio will be changed. So that is why considering same compression ratio is not an ideal case, rather you can consider same peak pressure, and for that we will be able to show that efficiency of the diesel cycle greater than dual, greater than Otto. So with this I stop here discussion today, and I will continue our discussion in the next class. Thank you.